Thank you very much, Ben. Let me start by thanking the organizers for giving me the opportunity to present some of my work here and also for facilitating an online seminar. As some of you know, I have a 6-week-old baby at home, so I couldn't travel. So today I'd like to tell you a little bit about some work that I've done recently in collaboration with Marga Minucci, Rodrigo Banoso Macedo, and Laura Sberna in this paper here, as well as some upcoming results with my PhD student, Giulio Daiocci, on quasi-normal mode orthogonality products in hyperboloidal foliations. So let me jump right in. So the main character in the talk today are quasi-normal modes, and as Aristos introduced this morning, these are essentially characteristic oscillations that control the response of a black hole system to linearized perturbations. And over the years, they have attracted a lot of attention in the literature, mainly because they contain intrinsic geometric information about the black hole spacetime itself. And as a result of that, they have found lots of applications in a variety of directions. For example, in astrophysics, people use quasi-normal modes to study the ring-down phase that comes after a binary black hole merger. In mathematical relativity, quasi-normal modes are used, for example, to study the well-posedness of certain initial problems. Quasi-normal modes are also used in addressing more fundamental questions in gravitational physics, and here I have in mind things related to quantum gravity. And last but not least, quasi-normal modes have found applications in the gauge gravity correspondence, which is the most relevant application for the audience today. So as Aristotle was saying, quasi-normal modes control the response of the dual or strongly coupled field theory to perturbations. Okay. Now, despite the fact that quasi-normal modes have attracted all this attention in the literature over the years, there is one fundamental aspect of them that hasn't been fully developed yet, and that is the fact that quasi-normal modes actually arise as eigenmodes of a non-normal operator. This is a simple manifestation of the fact that in a black hole system is a dissipative system. So if we are in ADS, we are losing energy through the horizon. If we're in asymptotic flatness, we lose energy both through the horizon and asymptotically. And this implies that the evolution operator of the system is in fact non-normal. And when this is the case, it means that the so-called spectral theorem does not apply, and this has important consequences. But before I tell you a little bit more about these consequences, let me take a step back and remind you what the spectral theorem says. So the spectral theorem says that if we're dealing with systems that are described by a normal operator, and I define here what I mean by normal, it's an operator that commutes with its adjoint. And remember, in order to define the adjoint, you need to have an inner product. So in systems that are captured by this normal operator, then we know that the eigenvalues of such an operator are stable against external perturbations, and that the eigenvectors are orthogonal to each other and they form a complete basis. Now, in the opposite case, when we're dealing with a dissipative system, like for example, a black hole that is captured by a non-normal evolution operator, then the spectral theorem does not apply. And what this means is that the eigenvalues of the system, which are now complex, can be potentially unstable to external perturbations of the theory, and that the eigenvectors are now neither complete nor orthogonal to each other. Okay? So, and in everything that I've said here, it's important to emphasize that we are taking into account an inner product that is physically motivated, for example, the energy inner product, when we make these statements. Now, for the context, in the context of black hole physics, as I was saying, the lack of the spectral theorem had important consequences, and to date, two of them. The first one is that indeed the spectrum, so the frequencies of the quasi-normal modes, are indeed unstable to external perturbations of the theory. This is fairly well established. It has been seen in a variety of black holes in different dimensions, different asymptotics. So that's well established. What's not that well established is the physical consequences of the spectral instability, as well as what is the imprint of this instability on time domain computations. Okay. The second consequence has to do with the appearance of transients. So transients are dynamical effects that are precisely rooted in the fact that quasi-normal modes in this case are not orthogonal to each other. And effectively, they describe situations where a small perturbation if we do the linear time evolution, they start very small and then they grow for a certain period of time, and only at later times they start to decay according to the lowest lying quasi-normal mode. Now, if this growth is large enough, this can trigger nonlinear effects, and this is precisely what triggers the onset of turbulence early in fluid dynamics. And similar transient effects can appear in principle in black hole physics as well. Now, in this talk, following the work of these people before us, we want to ask the following question. So can we define a non-traditional, not physically motivated product under which quasi-normal modes appear to be orthogonal to each other? And if we have such a product at hand, can we use it to define excitation coefficients? So even though quasi-normal modes will not form a complete basis, at late enough times, we do expect the field to be approximated by a sum of quasi-normal modes. And here, the excitation coefficients essentially capture how much of each quasi-normal mode is contained in the field in that regime. So these are the two questions that we want to ask. And the answer is yes to both questions. So we can construct products under which quasi-normal modes appear to be orthogonal, and we can indeed define such excitation coefficients. In doing this computation, I will be using hyperboloidal foliations. The reason for this is that non-model physics appear more natural in these coordinates. And I'll say a couple of words more on this later on. For the sake of simplicity, we'll be focusing on the massless scalar case in Schwarzschild black hole. And all the statements that I'll be making are general enough. So in principle, they don't depend on the space-time asymptotics. Having said that, we have only tested the formulas numerically for the case of ADS and flat space. But in principle, they should apply for de Sitter as well. And with that, let me move on to describe three ingredients that I will need in order to explain the orthogonality product we came up with in full glory. The first ingredient is, as I was saying, hyperboloidal foliations. So instead of doing the computation in coordinates t, r, theta, and phi that Aristos introduced this morning, I will be going to hyperboloidal coordinates. And in fact, I'll be doing two different coordinate transformations, one that will be taking me to future hyperboloidal coordinates, and one that will be taking me to past hyperboloidal coordinates. Okay, so in both cases, the original coordinates are related to the new ones through the so-called height function h. This is a fully known function. I just didn't write it here for simplicity. And the only difference between the future hyperboloidal coordinates and the past hyperboloidal coordinates is that t goes to minus t and phi goes to minus phi. Okay, and it turns out that this t phi to minus t minus phi is in fact a symmetry of the metric, which I will denote as a curly j. And what this curly j does is effectively taking us from future hyperboloidal coordinates to past hyperboloidal coordinates and vice versa. Now, the importance of this symmetry is that it actually maps quasi-normal modes to anti-quasi-normal modes. Quasi-normal modes are regular in the future hyperboloidal coordinates. They are very well behaved on the future hyperboloidal foliations. While in the past hyperboloidal foliations, what is regular is instead the anti-quasi-normal modes. So if we take anti-quasi-normal modes and we write them in terms of these coordinates, rather the natural ones, they will be divergent, okay? So bottom line, the J symmetry essentially takes quasi-normal modes to anti-quasi-normal modes and vice versa. So that's the first ingredient. The second ingredient is the Hamiltonian. So as I was saying earlier, we'll be dealing with the simplest case, so a massless scalar field governed by the Klein-Gordon equation. So if we rewrite this equation in hyperboloidal coordinates, we take out some powers of r so that the field is order 1 asymptotically, and we do a time reduction to bring the system down to a first order formulation. We get an equation that looks like this, and from this we can easily read out the Hamiltonian of the system, which now takes the form of a 2 by 2 matrix of operators. And here L1 and L2 are fully known operators. I didn't write them down for simplicity. Now, earlier I said that in hyperboloidal coordinates are better suited for discussing non-model, non-normal physics. And it's precisely because all the information about the leakage of energy, we know where it comes from in these coordinates, and it comes from this operator L2. Okay. So one more fact that we'll need later on is that this Hamiltonian here actually anti-commutes with H. So it satisfies this relationship here. And in order to see that, it's very simple. You just start from the equation of motion and you apply J, you go through the transformations, and you see that you get a minus sign appearing in front. So JH is equal to minus the reverse. The third ingredient, which is vital for the construction here, is conserved currents. So in this case, we'll be considering two currents, the symplectic current that Polydorus actually touched upon earlier today, and the energy current. So the symplectic current is constructed in this way using two solutions, psi1 and psi2 of the Klein-Gordon equation. And when we put the two fields on shell, this current here is divergence free, so the current is conserved. The energy current instead is constructed by taking the stress energy tensor of the scalar field and contracting that with the timeline killing vector. Now, when you do that, you get a current that is actually quadratic in psi, it goes like psi square. But for the purposes that we want, for the orthogonality product, we need something that goes like psi1, psi2. So we start from this and we do the natural thing to promote the energy current to a bilinear energy current in this way, making sure that the expression here on the right-hand side is symmetric between psi1 and psi2. Okay, and once again, this current is conserved on shell. Now, when we have these currents at hand, a natural thing to do is just to go and integrate them on a constant tau surface, which I denote here by sigma tau, in order to get this bilinear form, which is a function of psi1 and psi2. Okay, and here, in order to be able to do the integration, I need to dot J with the normal vector on that surface. Okay, now two comments are in order. The first one is that the bilinear coming from the symplectic current and the bilinear coming from the energy current do look very different to each other, but in fact, they are related. So if I take the symplectic bilinear and in the second entry, instead of putting psi2, I put the time derivative of psi2. So I act on the second entry with the time translation operator, then I get the energy bilinear plus some boundary terms. What this expression teaches us is not only that the symplectic bilinear and the energy bilinear are related to each other, but we also learn that if we apply a series of symmetry operators here on the second entry of the symplectic bilinear, we can get an infinite tower of bilinears that we can use in our construction. Okay, so that's the first comment. The second comment is that pi, as defined on the previous slide, is not conserved. And this is a simple manifestation of the Gauss law. So if we take pi and we value it on a surface at tau 0 plus delta tau 0 being constant, and we subtract pi evaluated on this surface here at constant tau 0, then that will be equal with the fluxes of the current through the two boundaries that are located. Yeah.
Your head is covering the diagram at the
Oh,
moment.
yeah. Sorry, I can't actually see myself. Sorry. Yes, so I was saying that pi evaluated on this surface minus pi evaluated on this surface has to give the fluxes through the two boundaries at sigma is 0 and sigma is 1, just because because of the Gauss law. Okay, and here the fluxes are evaluated in this way. So it's the integral of the current now along a surface of constant sigma. And in order to do that, we need to introduce the normal vector to that constant sigma surface, which I denote by SA. Now, for later convenience, this expression here can be written in terms of time derivatives in this way. So the time derivative of pi is equal to the time derivative of the fluxes through the boundaries. Okay, so this is the second comment. And with that, we have everything, all the ingredients that we need to introduce the orthogonality products. And it turns out that there are two ways to actually achieve an orthogonality product. The first one is just to take the bilinear form that we introduced on the previous slide, act with the symmetry J on the second entry, and that will give you an orthogonality product. Okay. Now, the interesting thing to point out here is that if psi1 and psi2 are Gauss-Normal modes, then that orthogonality product will be equal to the computation of the bilinear product with Gauss-Normal mode 1 and anti-Gauss-Normal mode 2. And remember, here we're dealing with future hyperboloidal surfaces. So we are computing. Yeah.
Can you remind us of the definition of anti-Quasi-Normal mode?
Yes. So if you have for a Gauss-Normal mode, you have energy going in the horizon, okay? And it's regular on the future horizon. If you have an anti-Gauss-Normal mode, you have the opposite boundary conditions at the horizon, and it's regular on the past horizon.
Okay, thank you.
Yeah. And as I was saying a few slides ago, the symmetry J, what it does, it maps a Gauss-Normal mode to an anti-Gauss-Normal mode. That's why the comment here. Now, what I was trying to point out is that on a future hyperboloidal surface, psi1, a Gauss-Normal mode, is regular, but an anti-Gauss-Normal mode now diverges. So this bilinear, the integrand of it is divergent, and we have to find a way to regularize it. And I'll say more about that in a minute. Now, the next thing to do is to check how the action of the Hamiltonian works on the orthogonality product. And we do this in two steps. First, we consider the action of the Hamiltonian on the bilinear, and this is what we get. So acting with the Hamiltonian on the first entry plus acting with the Hamiltonian on the second entry gives us 0 plus some boundary terms. Now remember, J and the Hamiltonian anti-commute. So if we take into account that anti-commutation relation, we get an expression like this. So the Hamiltonian acting on the first entry of the orthogonality product is equal to the Hamiltonian acting on the second entry of the orthogonality product plus some boundary terms. So if magically, or not so magically, manage to find a way to get rid of these boundary terms, then we'll have an expression that looks like this. So the Hamiltonian acting on psi1 is equal by definition to the adjoint of the Hamiltonian acting on psi1, which means that the Hamiltonian with respect to this orthogonality product is formally self-adjoint. And from such an operator, one would expect quasi-normal modes to be orthogonal to each other. And this is actually quite easy to see. So when we act with H on psi1, we get a factor of the frequency of the first mode. When we act with H on the second mode, we get the frequency of the second mode times the product between the two modes. When we're dealing with two modes that are the same, then this first term vanishes. So this equation is satisfied. When the two modes are different to each other, this term here has to be 0. Okay, so in this sense, we get orthogonality of Gauss-Normal modes. Now, I need to tell you what way we have found to get rid of these boundary terms, and this involves analytic continuation. And we actually found two different strategies to do that. The first one is to go to complex sigma and deform the integration contour in such a way to get something that is regular. And as an example, here on the right-hand side, I'm plotting the integrand of the orthogonality product for one of the cases that we checked. And you see that we have a very complicated structure of the integrand, and specifically, we have a branch cut along this line here. Okay, so the contour that we use essentially goes around this branch cut, and this gives results that are nice and regular and get rid of the boundary terms that we wanted to get rid of. The second strategy is, in fact, semi-analytic. So what we do is we do a Frobenius expansion close to the horizon. So we write the Gauss-Normal modes as a series in 1 minus sigma. We plug that back into the integrand. We massage a little bit the formulas, and we get something that looks like what you have here on the right-hand side. Now, this integrand in integral is actually a known function. It's the trigonometric hypergeometric function. Now, the only problem is that this function is convergent only for certain values of a. And a, if you do this calculation in detail, turns out to be related to the frequency of the Gauss-Normal modes. So in order to get this expression to converge, in our case, we need to do an analytic continuation over the frequencies. But both strategies actually work, and as I will say later, they actually give us consistent results. Now, as I was saying, we found two different ways of introducing the orthogonality product. In the first case, we essentially use analytic continuation to get rid of the fluxes. In the second case, we actually incorporated the fluxes in the computation itself. So rather than dealing with the bilinear pi that I introduced earlier, we deform it to pi tilde, which is equal to pi minus the fluxes. Okay, so if we check the time derivative of pi tilde is 0, so pi tilde is conserved. And if we check how the Hamiltonian acts on this bilinear, this extended bilinear, we see that the Hamiltonian acting on the first entry plus the Hamiltonian acting on the second entry gives us 0. So in this case, we do not have any boundary terms. So we don't need to do any analytic continuation in this case. So given this extended bilinear, we actually introduced the extended orthogonality product in the same way as we did before. The product is now defined in terms of pi tilde with the J symmetry acting on the second entry. And precisely because of the anti-commutation relation between J and H, we get an expression that looks like this, which means that Gauss-Normal modes, when we apply this expression to Gauss-Normal modes, we get Gauss-Normal mode orthogonality. So this is all the abstract, or if you want, the mathematical formulation. And what we did was to go and test these results numerically. And we tested them in two situations. On the one hand, we tested it for scalar Gauss-Normal modes in this Schwarzschild black hole in asymptotic flatness. So we confirmed that the product between two Gauss-Normal modes appropriately normalized thus gave us a delta function. They are orthogonal to each other. And as I was saying a moment ago, we got all the results that we got turned out to be consistent with each other. So we did the calculation for the energy current, for the symplectic current, with two different analytic continuations, the complex contour and the semi-analytic approach, and everything agreed as well with the generalized orthogonality product. So this was the first computation we did numerically. The second one was to precisely check orthogonality for scalar Gauss-Normal modes in ADS asymptotics. So we did that for the BTZ black hole and for this Schwarzschild in 4 dimensions. So this is all I had to say for the orthogonality product. Let's now move on to talk about excitation coefficients. Now, there is a big disclaimer here that even though we were able to introduce this orthogonality product, according to which Gauss-Normal modes appear to be orthogonal, the problem overall is not self-adjoint. We do not have a self-adjoint system. So the product we've introduced is not positive definite, and the weight is complex, right? So, and precisely because we do not have a self-adjoint system, this was all essentially, if you want, a trick. The system itself is not self-adjoint. We do not expect Gauss-Normal modes to form a complete basis. And it's not as simple as adding anti-quasi-normal modes because those blow up in the future hyperboloidal coordinates. Now, nevertheless, as I was saying earlier, we do expect quasi-normal modes to approximate a solution well enough at late times. So a solution of tau and sigma at late times should be able to be approximated by a sum, like what you see here, in terms of quasi-normal modes psi I with some coefficients Ci that are the excitation coefficients. Now, the honest way of computing these excitation coefficients is to go and compute the retarded Green's function and get the residues at the poles of that retarded Green's function. But it turns out that if instead we take our orthogonality product and we compute this quantity that you see here, so the projection of the initial data to the quasi-normal mode appropriately normalized, we get the exact same values as with the original calculation that I described. Okay, and we did test this numerically. So we computed excitation coefficients for proof of principle initial data, the simplest possible you can imagine. I have it here for this Schwarzschild black hole in asymptotic flatness, and we did see agreement. Now, a small issue comes when discussing excitation coefficients, well, not so small, when we're discussing excitation coefficients for the extended orthogonality product, because in that case, the fluxes are more globally defined in time, and we were unable to compute the excitation coefficients. But this is still, we're still trying. And with that, let me summarize and conclude. So today I've shown you that we have constructed a number of orthogonality products, and using those products, one can define excitation coefficients. And the formulas that I showed you, we have tested them for flat space and ADS, and they work. The expectation is that they're more universal. Now, in terms of things to do, well, the most natural continuation of this work is to actually repeat it for different types of perturbation rather than a simple scalar field. And this will be very relevant for people studying the ring down for metric perturbations around a Kerr black hole in asymptotic flatness. But of course, there are lots of other directions that are equally interesting. First of all, understand the connections between the product that we introduced and the Keltish formalism and the other orthogonality products that people have constructed. Really understand the role of the fluxes in these constructions and their role in the regularization and certain Green's function techniques. And last but not least, understand how things change if they do close to extremality. And with that, let me thank you and stop here.
Please.
Hi, Christiana. I have a question. I like it when quasi-normal modes collide.
Yes.
What happens to your construction when you have such a collision between quasi-normal modes?
That's a very good question. We don't actually know. No one studied that.
Okay.
I have a question as well. So in take the ADS case, and imagine you have a holographic quantum field theory dual to that. And you talked about computing excitation coefficients. Is there a sense in which we can compute, whether these products would be useful for doing a similar thing in the QFT?
There should be, but I don't know how to even begin formulating that question. In principle, the excitation coefficients are also interesting in understanding interactions between quasi-normal modes, but that hasn't been explored. But yeah, I agree with your statement. These excitation coefficients should be useful for the dual field theory. How exactly? I'm not sure.
I just want to follow up because I understood that the construction is not complete. So this base is not complete. So there might be, it seems to me that I might have modes that are not completely expandable in these bases, right?
Yes.
So in particular, I might have things in field theory that cannot be nicely decomposed in quasi-normal modes.
At generic times, yes. At late times, we do expect the quasi-normal modes to be good description. So I think Ben's question was within that regime.
I think it's always, from what I know, it's the only regime applicable in holographic quantum field theory is this late time regime. Like, I think there's only quasi-normal modes actually in holographic examples. Like, this early time region is the boundary theory doesn't see it somehow. But anyway, that's okay. Any more questions? All right. Well, thank you, Christiana.
Thank you.
There again.
Fine.
Okay.
I should share my screen.